Hey folks, so a very important skill that you should develop in calculus is to know a few important graphs associated with the function and to know them back and forth. That is, if you see a graph, you know it's the function. If you look at the function, you know the graph. So let me walk you through this worksheet a little bit here. So this is a 2-page worksheet. You can print one out yourself that is on Canvas. So after you do that, think about this. There is a thing called a power function, and a power function is of the form f of x equals kx to the p, where k and p are constants. And constant just means that it's a number. And you can choose any real number at all, and that would be a power function if it fits this form, f of x equals kx to the p. So which of these functions that we have on these 2 pages are power functions? That's the first question I have for you. Pause this video for a moment and look over them and try and select from the definition which one are power functions. So now that you have looked over it, let's look at constant function. Is a constant function a power function? Yes, it is actually, because if you wrote this in this form, times x to the 0, remember that x to the 0, let me zoom in a little bit here, remember that x to the 0 is equal to 1. So this would create that function, the constant function. So yeah, it's in that form. So this is a power function, the constant function. Over to the right, this linear function, y equals x, it could also be written in the same kx to the p form, where k is 1 and p is 1, and that would create f of x equals x. The absolute value cannot be written as a power function, so this is a no. And the quadratic here, that's a yes. That can be written, of course, as 1 times x squared, where, of course, the p is 2 and the k is 1. And the cubic can be written as a power function, 1 times x to the 3rd. That means that p is 3 and k is 1. So that is definitely it. What about the square root function? Can you write it as a power? Well, you can if you allow for the exponents of fractions, which we do allow in a power function. So I'm going to write x to the 1/2, and so yes, it does qualify, because if p is 1/2 and k is 1, it is a power function. So a lot of these, as you can see, are power functions. How about y equals 1 over x? And if you think about it, this could be written 1 times x to the -1. So if p is -1 and k is 1, that is a power function. The natural log, however, cannot be written as a power, so this one's not a power function. Looking at arctan, that is an inverse tangent. Inverse tangent function cannot be written as a power, so this is not a power function. Next door to it, though, and it looks really similar. These two look really similar, but they're very different. And the one right next door is the cube root, and if you write this as a power, it would be x to the 1/3. So it is a power function. Looking at the next two, these are exponential functions. Exponential functions are not power functions. Exponential functions have the variable in the exponent rather than the variable as the base. So coming back over to our example here, notice that x is the base, and that's what makes it a power function. It's a base to a constant number. But if you look at an exponential function, the base is the constant, and the power, that is the exponent, is the variable. So it is not a power function to be an exponential function. Then you might recognize your trig functions, cosine and sine. They come up a lot in calculus, so do get those memorized in their general look. And finally, we have tangent and cotangent. None of these trig functions are power functions. These are all trig functions. So they stand alone in their own class as trig functions. What is interesting in trig functions and rational functions is the idea of an asymptote. So if we look at tangent, there are an infinite number of asymptotes. What's an asymptote? Well, it could be vertical or it could be horizontal, but an asymptote is a line that a curve approaches. So if we looked at this, do you see how this curve is being approached? The line is being approached by the curve in both directions, right? So you have a vertical asymptote right here at x equals pi over 2. And if I come over here, you can see it happens again and again and again. And it happens every pi jump, an additional pi. So if I add pi to pi over 2, then I get 3 pi over 2. And that is the next asymptote. This describes, therefore, right there, all asymptotes for tangent. Cotangent, similarly, you have these vertical asymptotes here. Again, here, you get them every pi, but when you add 0 to pi, or if you subtract it, right, so minus pi or plus pi, that gets you all the asymptotes. So we have pi plus pi k, or you could just actually just say k times pi, and that would do the trick as well. Looking back, though, at arctan, let's go back here. Arctan. Arctan has a horizontal asymptote. The curve approaches this both horizontal lines here. It's bounded above and bounded below, and the curve approaches pi over 2. This is arctan, and it approaches negative pi over 2. So this is a horizontal asymptote. And so some graphs have both. Some graphs have both horizontal and vertical asymptotes. This one just has a couple of horizontal asymptotes. Okay, and these are just vertical asymptotes down here. And let's look back at our first page and see, are there any asymptotes on any of these graphs? And if you look through here, there's no asymptotes in any of those above graphs, but you can see that the 1 over x function, it does have this vertical asymptote. So if we have a vertical asymptote, then the equation will always be x equals, and whatever number then is goes through the x-axis of that vertical line. So x equals 0 would be the equation of that vertical asymptote. And the natural log function as well has a vertical asymptote. This looks like it touches, but it never touches. The curve never touches that vertical line. So that makes it an asymptote. And once again, you have a vertical asymptote of x equals 0. So know your graphs, walk through them, know them well, get them memorized. We'll be using these quite a bit in this class. And it's always a good idea to be able to pull them forward in your head really quickly. Okay, I hope that helps.